double bond O or O, this bond, this is correct. Otherwise, what happens? This one will be the correct structure. Which one will be the correct one? Anybody? Because you have to, we can't write like that. If you see what happened, anybody can't write like this. This is not correct structure of ozone. Why? Because if you write like this, what happened? The central atom is getting how many electrons actually here? 10 electrons. For oxygen it is not possible. For sulfur it is possible better. The elements which are present in the third period, remember better, the elements which are present third or after the third period, they may have more than 8 electrons because they are having extra d orbital will be there. Understood here? The elements which are having in the third period, having d orbital, they may have more than 8 electrons. No problem. For sulfur, for phosphorus, we have seen this one. To observe here what happened. This one. See here, phosphorus, sulfur. These are third period elements. Which period they are? Third period elements having d orbitals are there, empty d orbitals are there. These are having empty d orbitals are there. So they may get what? 10 electrons, 12 electrons, isn't it? In their configuration. There are more than octet configuration is possible for which period elements? Third period elements, right? But for oxygen, which period element better? Oxygen?
The second.
Second, does it have d orbital in it? Is it having d orbital? Yes?
No, sir.
No, d orbital? No d orbital. It is not having the d orbital. So you can't write more than 8 electrons, isn't it? You can write how many? You see. 2s, 2p. Okay, otherwise you remove this one. Now here you can remove, accommodate 2, here you can accommodate 6 only. Correct or not? In p orbital, you can accommodate 6 electron. In s orbital, you can accommodate 2 electron. Total, we can accommodate 8 electrons only. So this structure will be ruled out here. You can't write like this structure. Why? Because here the 2 electrons, one bond carries how many? 2 electrons here. So there are 4 bonds are there. 4 into 8 plus 2, this one, total 10 electrons are there here. So this structure you can't take. Now here you can take this structure. Why? Because here what happened? 3 bonds are there. 3 to the 6 plus 1 lone pair, 8 electrons are there. And here also what happened? 3 bonds are there. 3 into 2, 6 electrons and 1 lone pair, 8 electrons. Now these 2 structures will be okay. These 2 structures will be okay for what? Oxygen. Because oxygen maximum it can accommodate 8 electrons. Understood here? Now once we study what happened, yesterday I told you how you study this bond length, everything by using the X-ray diffraction methods or spectroscopic methods. In that method, what you are observing, the OO bond length, if you observe what happened, that you are getting around 128 picometer. The bond length, if you study here by the spectrometer or extra diffraction methods, the OO bond length, how much you are getting here, beta? 128 here. The OO bond length, experimental result, OO bond length, how much you are getting? 128 picometer. For both here or here. Here you are getting how much bond length? 128. And here you are getting how much here? So the double bond length always will be what? Lesser than the single bond. Yesterday I told you, because double bond, if you get what happened, the bond will compress. So when you get a double bond, the bond length should be 121 picometer. That means O double bond should get how much bond length actually? 121 picometer. And a single bond, and that is having what? 148 picometer. Okay, single bond, OO bond length, if you observe what happened, how much it is? 148 picometer. So here again I am saying here, for double bond character, the bond length must be 121. Theoretical result it is. It's a theoretical values. For single bond, OO bond length will be 148 picometer. But when you see experimental result, both are having 128 picometer, 128 picometer. How it possible? Anybody? How it possible? Reply. कुछ तो बोलो. How it possible? Sleeping.
Sir, O3 molecule are intermediate between double and single bond.
This is because of what? Resonance. This is resonance is the reason actually. So now we are studying the resonance now. So when you observe the ozone structure, one is having double bond character, other is having what? Single bond character. For single bond, the bond length is what? 148 picometer. For double bond, the bond length must be 121 picometer. These are theoretical values. But experimentally, by the X-ray diffraction methods, the bond length in the ozone, both are having same. This one and this one, both are having same. That is 128 picometer. What is the reason if they ask? The reason simply what you have to give? Resonance. Isn't it? Resonance. You said something about intermediate. Intermediate we can say. Why? Because of the resonance. Because of resonance what happened? Neither it is having single bond character, nor it is having double bond character. Intermediate properties between single bond and double bond. That is the reason what happened. 128 is between what? 121 and 148. Right? So this is the explanation. On examination, if they ask what happened, the resonance structures, you have to write what? How to write this one? Resonance structures, you have to write this one actually. And again, I will write this one. Here I will write that one. How to make in the exam, how to write the resonance structures, let me see now. First of all, you have to write like this. Oxygen, oxygen, oxygen. Put double bond here, put double bond here. This is a day 2 bond beta. What is a day 2 bond means? One will donate and both will share. We'll get again in last chapter. At the end of the chapter, we get this one. No problem. Now, oxygen, single bond, double bond. Here it will be day 2 bond. Now here I am writing like this. Now both can be represented like this also. Oxygen, oxygen. Now here you are having a pi bond, correct? And here also you are having the pi bond. Right. Now what I am doing here, that pi bond I am writing like this. Here I am writing that pi. Like this. Now this is because of the resonance. This is the resonance hybrid orbit. I can write here what? Resonance hybrid orbit. In this way we can show the, if they ask, write the resonance structures of ozone, you can write like this. For this one, how much beta? 121 picometer. For this one, how much beta? 148 picometer. And actually you are having how much here? 128 picometer like this here. Right? So let me see this one here. Just definition of it. What is the definition of resonance? Based upon the example, now we go for definition. From here it is. According to the concept of resonance, whenever a single Lewis structure cannot describe the molecule accurately. For example, you take the first structure here, this one, the first structure here. This is not explaining all the properties of ozone. Only this one structure. Based upon only this structure, I cannot explain the ozone properties completely. Because here you are also having double bond. So if I want to explain the double bond character of here, this one, if I take what? 1, 2, 3, I cannot explain the double bond character between second oxygen and the third oxygen. I can only explain the double bond character of second and first oxygen. I cannot explain the double bond character of second and third oxygen. So I can't take this one singly to explain the ozone properties that they are saying actually. Understood here? Single Lewis structure cannot describe a molecule accurately. A number of structures, that means more than one structures with similar energy of the nuclei, bonding and non-bonding pair of electrons are taken as the conical structures of the hybrid, which describes the molecule accurately. That means what happened? I have taken how many structures here? 2 structures I have taken. Structure number 1, structure number 2 I have taken. Now these 2 structures, in which what happened? The position of the electrons you can't change actually. See, the position you can't change. The position of the nuclei, the position of the nuclei we can't change. And the energy both should have almost the same energy. And the bonding, non-bonding electrons must be what happened? Same. You can't increase or you can't decrease the number of bonding electrons here. For example, if you observe here what happened, how many bonding electrons are there? If you observe here what happened, total number of bonding electrons I am not changing it. When you observe what happened here, same number of electrons you're having. Here also what happens? Same. The number of total number of electrons, what happened here? The remaining change only, same only actually. Understood here? So when you're writing the two or more resonance structures, what happened? The non-bonding electrons must be what happened? Same. And even what? Bonding electrons also. That means the bonds must be same. You see how many bonds are there, beta? 3 bonds. Here also what happened? 3. That means the lone pair number of electron must be same. And the position of the nuclei must be same. And the nuclear energy also should be almost similar. Not similar, almost should be similar. In that way only we can make the 2 or more number of resonance structure. And these should describe the molecule accurately here. So this is called what actually? Resonance structure. What is the meaning here? Very simple. A single structure is unable to explain here. So what we are taking here? 2 or more resonance structures we are taking to explain the molecule. Right? The best example you have taken is what? Ozone molecule. Understood here? Right. Now we'll take what? One more structure here. CO3 minus 2 I have taken. CO3 minus 2 I am taking. Okay. Now let me see how it is. CO3 minus 2 we'll discuss that on PPT like this. Now if you observe here what happened, I will take an empty paper here.
Excuse me, sir.
Bolo beto.
Sir, in resonance only conical structure is possible.
Yeah. Conical structures are nothing but what? That electron distribution in structures. So that that because of resonance, pi conjugation, we get that one. That we'll discuss in organic chemistry in detail, but here we get only for some molecules.
Okay, sir.
Right, so we'll see now here. Now all of you please read this definition, same definition, right? All of you read your definition in textbook, all of you. Now this is the resonance structures we have taken for this one, you see. All are having what? Same type like this. Bond angle it is 116.78 is a bond angle. You have taken these resonance structures. Now, what are this information we'll see before after completion of the CO3 minus 2. So let me take the CO3 minus 2 like this. CO3 minus 2. Now I'm writing the CO3 minus 2 first of all. Right. CO3 minus 2. First of all, you have to make a Lewis structure. Carbon, central atom, and remaining 3 oxygens you can place like this in the trigonal planar way. You can place like this. Minus 2 means it has some extra 2 electrons. Correct? Now, carbon valency electrons are how many beta? 4. Put here what? 1, 2, 3, and what here? 4 electrons, right? Correct? Carbon electrons valency kitna beta? 4. 4th A group element 4. Understood everyone? Next. Oxygen valency many times I discussed here 6 electrons. Correct? Right. Now extra 2 electrons are there? No. Minus 2. Extra how many electrons beta? Extra it is having?
2, sir.
2. Now that extra electron I am putting here. Extra 1 electron, extra 1 electron. Right? Now again oxygen has how many? 6 electrons I am putting here. The oxygen electron 6 electrons I am putting here like this. The oxygen 6 electrons I am putting like this. Now when you observe here, all elements, because carbon, which period element beta? Carbon and oxygen, which period beta? Second period. And absence of d orbital. absence of d orbital. So I can accommodate only 8 electrons around the central atom. And even what happened? Surrounding atom. Mostly what happens? Central atom. Now, this structure explains the octet configuration of the carbon. You see here 1, 2, 3, 4, 5, 6, 8 electrons it is having. It is having total 8 electrons. Here 2, here 2, here 4. In total what happened? 8 electrons. Now this is the reason we are taking the structure like this. Now what I am doing here I am making a single bond and pi bond like this, right? And this one will be the day 2 bond like this. This one will be the day 2 bond like this. Now oxygen electrons are not utilizing, same like that. Now what I am doing here, you may say whether pi bond will present on always first oxygen. No, you can't say like that. All oxygens may get the pi bond here. That means what I am doing here, I am writing the resonance structures. Based upon this what happened, now I will write what? The pi bond on the second oxygen. Now I will make the pi bond on the second oxygen, so that what happened, first oxygen and third oxygen will have single bond. Okay. Then after that, whether even what third also will get the pi bond now. Even third also getting what? Pi bond now. So I am writing the pi bond on the third oxygen also. Right? I am getting the pi bond on first oxygen. I got the pi bond on second oxygen. And I got the pi bond on third oxygen. That means pi bond is present in all oxygens. So based upon what I can write here, so pi bond, single bond is compulsory. Now pi bond is present here, and the pi bond is here also is there, and the pi bond is here also. This is called a resonance hybrid orbital. Resonance hybrid orbital, we can write orbital structure, and these are called what actually? Resonance structures. How many resonance structures are possible, beta, for CO3 minus 2?
3.
3, sir.
Structures. Is it difficult or hard, beta? Sorry, easy. Difficult or easy? Very simple. If we know this structure, remaining 2 you will definitely will get. Remaining 2 definitely will get. Correct? Why? Because first oxygen double bond, then second double bond, and third double. Remaining one will have single bond. In this way, if you remember what happened, you can examination, you can easily write here. We'll take one more structure also, that is called HNO3 structure. HNO3 also we can take it. Now you have to remember this structure. Then what happened? What you have to do here? Very simple here. You are having a pi bond here, right? Make the pi bond here. Completed. So whatever the pi bond is there here, that you are shifting where? From here to what happened? Here. That is only the thing that, right? So now we'll see some important points about the, isn't it? Resonance structures here. They given here CO2 molecules also. This you can do very simple, no problem. Now, a resonance stabilizes the molecule as the energy of the resonance hybrid is lesser than the energy of the single conical structure here, isn't it? For example, this is a canonical structure of what? Ozone. This is the first structure of canonical structure of what? Ozone, right? Now, this will have more energy. This will have more energy when you compare with what? Stabilized resonance hybrid. This will have less energy. For example, for your understanding, I will make one more structure very, very simple. What is the name of this compound, beta? What is the name of this compound, beta?
Benzene.
Benzene. First one is benzene or second one is benzene, beta?
The first one.
Second one is what? Say what?
So both are benzene.
Both are benzene. Very good now. Now when you observe here what happened, both are undergoing resonance.
Benzene.
And here this pi bond is shifted here, and this pi bond is shifted like this, and this bond shifted like this. This pi bond shifted here, and this will shifted over here, and this will be shifted over here. You are going to get this structure. That means both will possible actually. Now which one is benzene means what? Both are benzenes. But I am representing like this. Why? Because a ring I am showing here, because the pi electrons are moving inside the ring actually. They are delocalizing in the ring actually. The pi bond is delocalizing in the ring. Therefore, I am showing like this. Now, among these, both will have more energy. Both will have what actually? more energy. But this will have what? Less energy. Why? Because the excess amount of energy they are having, that is useful for what? Delocalization of pi electron. Now what happened? The pi bond here shifted to here. So because of pi is shifting to here, what happened? It lost some energy. It utilized some energy. Because of losing of energy, what happened? It get the stability. In the first class only we discussed how do molecule will get the stability. Because by what? Losing the energy. By losing the energy or by gaining the octet configuration. These are the only two things we discussed actually. So here also, when they form resonance hybrid structures here, isn't it? When they are forming what different type of conical structures, what happened? Their excess of energy will be utilized here and they become stable actually. In the ozone also same thing is happening. In the previous also we have discussed what happened. CO3 to know. Whatever the excess of energy they're having, they utilized for this type of resonance structures. Now what happened? The molecule is getting the stability because of the resonance. So this is the saying in this one. So what they are saying here, resonance stabilizes the molecule. Because of the resonance, it will stabilizes the molecule as the energy of the resonance hybrid is less than the energy of the single conical structure. This is the resonance hybrid. This one is the resonance hybrid. This is having less energy when you compare single canonical structures. These two will have more energy. But once they participate in the resonance, what happened like this, then they lose their energy, they become stable. The second point, if you observe here, resonance averages the bond character as whole. You see here again, the bond length here 121, the bond length here 148. So average value you are getting how much? 120. You may say, sir, 148 plus 121 divided by 2, we get them different thing. No, something what happened? 169 by 2, that is something around 170. That should be what? 135, some 135.5 like, sorry, not 135, something around what? 88 point something like that. No, sorry, this one is 268. No, some correct only 170 something it should have. Oh, sorry, 100, 200, 269. So 138 should have something roughly 138 picometer. But we are not taking the average value beta. 138 average value. We are not doing any mathematical operations. We are taking experimental result, isn't it? Simply we are not calculating averages. We have to go for according to what actually? Experimental result. Now experimental result is giving an average value in which you are getting 128 picometer. That means what is the meaning of this one? Pi bond is what? Dominating the single bond. So that is the reason what happens. Is near to what? Pi bond actually. 121 is a pi bond character, correct? So it is near to the pi bond. So we can't take what? The critical average value. Don't take critical averages values. Experimental averages we can take. Okay, so this is about the two things we have to remember compulsory. Okay, now these are the some micro misconceptions which are generally we have to remember for this one. So when you observe what happened, canonical forms have no real existence. If I say something, what happened? I want this one. Is it possible? I want only this one. I don't need this one. I want only second one structure. Is it possible? Only I want to isolate first structure. Is it possible? No, I cannot isolate the second structure. Is it possible? Second isolation? Impossible. So resonance structures are purely what happened? Hypothetical phenomena. Assumptions they are actually. They cannot be isolated. You cannot derive that one from the reaction. It's impossible to isolate them. They are highly what happened? Hypothetical structures. They could not exist, isn't it? The molecule does not exist for a certain fraction of time in one canonical form and for other fraction of time in other canonical forms. Okay, that means what happened? One to other always will changes. Like a fan will move. No, similarly, what happened? This ring always moves like this. Here. Like this, it is moving like the pi electrons are moving like this. Here. In this way, it is what happened? Permanently, it is moving like this. There is no such equilibrium between the canonical forms as we have between tautomeric forms and keto and enol form. If you, for example, keto and enol form, I will explain you later once we complete this one. The molecule as such has a single structure, which is the resonance hybrid of the canonical form and which cannot such as depicted by single Lewis structure. So we are not representing by single structure here. So okay, but we can represent like this here. Both structures can be represented like this. For example, if you observe what happened, benzene, this one. This is the representation we can do. Otherwise, for benzene, you can represent like this. Right? Now you see that the third point here, this is keto-enol tautomerism. I will explain here something. Keto-enol tautomerism, I will explain here. Let me see this. Now, these are the points actually we discussed just now. The canonical forms have no real existence. Resonance averages the bond characteristics as a whole number. Thus, the energy of the ozone resonance hybrid is lower than the other two forms here. Resonance stabilizes the molecule as the energy of the resonance hybrid is lesser than the single canonical structure. The molecule does not exist for a certain fraction of time in one canonical form and for other fraction of time in other canonical. That means the molecule does not exist in one form. Both will what happen? Interchange actually. There is no such equilibrium between the canonical forms, isn't it? Right. Now we'll see the keto-enol form I will show you. Now let me see this simple example I'm taking here. CH3 C double bond O H I have taken. Now I'm writing the hydrogen like this. Okay. Now what I'm doing here, I'm placing this single bond over here. Right? I'm placing the single bond over here. Immediately the pi bond will be shifted like this. So because of this, what we get? Something like this here. CH2 double bond CO minus H and H plus like this. And this H plus will move here. So we are going to get like this structure. CH2 double bond COH and hydrogen. This is called what? Enol form. Enol form it is. Because double bond is there, in, alcohol is there, ol. This one is called aldehyde form, aldo form. Okay, or keto form also we can take. If I take here CS3, that will be keto form. Now these are tautomers we can call. These are not resonance structures better. Tautomers better. Why? Because you are changing the position of the atom here. The atom position changed completely from carbon to what? Oxygen. But in resonance, what happened? We are not changing the position of the atoms here. Just we are interchanging the pi bond positions here. The position of the pi bond is changing, not single bond also even. In the resonance structures, only the pi bond position is changing. But tautomers, complete the position of atoms, everything is changing here. So tautomers can be isolatable. This you can isolate what enol, you can isolate what aldo form. This will be 99.9%. This will be 9.1% will be existence will be there actually. So tautomers can be isolatable because you are changing the position of the atoms there actually. So this is about the, isn't it? The resonance structures. Now in exercise you are having number of questions are there in exercise. See, I think have you completed this one? 4.9 I explained here. How do you express the bond strength in terms of bond order? Bond order, yesterday I told you, bond order is directly proportional to what? Bond strength. Yesterday only we completed this one. Define the bond length. Definition we completed. Explain the important aspects of resonance of CO3 minus. Just now we completed the CO3 minus 2 beta. And H3PO3 can be represented by 1 and 2 structure. So you have to give the answer for this one. Write the resonance structures of what? SO3, NO2 and NO3 minus. 4.13 resonance structures. HNO3, SO3 is very, very important beta. Complete this one. All these three. Lewis symbols. This is there in the first topic only. Lewis symbols for this one. 4.14 you have to compulsory complete this one. Okay. So today in this topic, what do you have to complete here? Yesterday topics also there. 4.9, 4.10. Okay. 4.9, 4.10, 4.11, 4.12 up to 4.9 to 4.14 complete. Okay. This exercise you have to complete today itself. Next we go for what? Next topic called polarity of the bond. What is the polarity of the bond? Let me see now. Now for example, if I write what happened, hydrogen, oxygen, chlorine, nitrogen, fluorine. I'm writing like this: hydrogen, oxygen, chlorine, or nitrogen, or fluorine I am writing here. Now tell me, in these two, which will get positive charge and which will negative charge beta? First hydrogen or second hydrogen? Which will get positive, negative?
Sir, second.
How do you say second? What is the difference between the first and second hydrogens? Yes. See, these are symmetrical molecules. You can cut into equal parts, correct or not? These are the symmetrical molecules. You can cut into equal parts here. Now you can't say which will get the positive charge and which will get the negative charge. These are all what? Non-polar molecules. Non-polar. They cannot develop the negative and positive poles here. Understood here? Hydrogen, oxygen, chlorine, nitrogen, fluorine, they cannot develop the polarities because they are symmetrical molecules. Their shared electrons are equally distributed, isn't it? Equally attracted. Here, this bonding electron, no. These two electrons are equally attracted by these two atoms. These electrons are what happen? Equally attracted here. Understood here? That is the thing you need to remember here. Right? Now let me see what is dipole moment and what is non-polar molecule. Everything we'll see now. So now dipole moment means what actually? What is the meaning of the dipole moment? Definition is very simple. Based upon the formula, we can make a definition. The product of the magnitude of the charge and the distance between the two centers of the positive and negative charge is called what? Dipole moment. Now very hard to understand here if you read like this. But if you make a definition by using a formula like this, dipole moment, charge into distance between the positive and negative charge. I will make like this here. I'm writing what happened, HCl I'm writing. Does it polar or non-polar beta, HCl?
Sir, polar.
Very good, because hydrogen is positive charge, chlorine is what? Negative charge. Therefore, definitely they are what? Polar molecules. For polar molecules only, they exhibit dipole moment. Non-polar molecule, dipole moment will be 0. Now, what I'm saying here, what is the meaning of dipole moment? Mu is just generally represented for the representation of dipole moment. That mu is equal to charge, positive, negative charge, into the distance between the positive and negative charges. Charge of the poles into what actually? Distance between the two charges here. If you multiply these two, that is called what? Dipole moment. You see here, the product here means nothing but means multiplication. Product means what here? Multiplication of the magnitude of charge and distance between the positive and negative charges here. Understood now? The definition is simple or not? The product of magnitude of the charge and the distance between the centers of positive and negative charge is nothing but called dipole moment. Now dipole moment mu is equal to charge into distance between the two opposite charges. Now generally the dipole moment can be represented by, expressed by the Debye units. It is useful for the MCQs here. What is the units for the dipole moment? Debye. Debye is the units represented by capital D. Now 1 debye is equal to 3.33 into 10 to the power of minus 3. It is not centimeter beta. It is C for charge, coulomb. For distance, meter. Okay. C for what happened? Coulomb. M for what happened here? Meter. So C for coulomb, M for what happened? Meter. 1 debye is equal to 3.3 into 10 to the power of minus 30 coulombs into meter. You have to remember this one. Is a very, very, very important formula for you. Right? Now, further if you observe here, it's a vector quantity. Vector quantity. I will explain vector quantity with an example. Okay? And it should be shown like this. An arrow mark like this. Crossed arrow mark like a crossed arrow mark. This is shown. And how we have to show? From positive to negative charge. From positive to negative charge you have to. For example, if I want to show dipolement, from where you have to show, from hydrogen to chlorine or chlorine to hydrogen beta? Yes?
Sir, hydrogen to chlorine.
50 only there. That means some students have no again left. Now to show from hydrogen to chlorine, like this is the showman. Always from positive to what? Negative. The arrow always should be shown from what? From positive to what here? Negative you have to show. For example, HF. This is positive charge. Chlorine is what? Negative charge. You know this one based upon group number. Higher the group number, higher the electronegativity of same period elements, isn't it? So this is about the dipolement definitions actually. Now already I told you 1 dB is equal to 3.3 and everything. Now for example, if I take what happened, water, H2O, water, I'm writing like this. Here I'm writing water, hydrogen, hydrogen. Now definitely oxygen is more electronegative than the hydrogen because hydrogen is having less electronegativity. Now here also what happened? Positive character. It is also what happened? Positive character. Now we have to show arrow marks like this here. Hydrogen to oxygen. Again what happened? Hydrogen to oxygen. And the resulting dipolement I can show something like this here. The resulting dipolement maybe show something like that because both will be added here. Cumulative, vector quantity, no, both will be added here. Now because of addition, what you are going to get here? 1.85 you are going to get. The dipolement, how much you are getting? 1.85 dB. This is a very larger value. That is the reason shown taken as a solvent. Generally, water is a universal solvent, we can call this one. Now, if you observe what happened in water, it's a bench structure. You have two OH bonds and bond angle is 104.5 degrees and it is having something around 1.85 dB. If you want in terms of coulombs, what happened? 1 dB is equal to how much? 3.3. So multiply that one with 3.3, you will get the answer in terms of coulombs and meters. So this will be useful for this one. Next, if you observe what happened, some structures I will explain here. In this one, I will explain. Now, if I take what happened, beryllium fluoride, BeF2, BeF2, beryllium fluoride. Okay. Now here it will be negative character. This will be positive because second group it is a seventh group element, right? This is the fluorine, right? Negative character. Now it is showing from which direction beta? Positive to negative, positive to negative. Now these two are same side or opposite side beta? The flow of electron same side or opposite side?
Opposite side.
Opposite
Now, whenever
side.
they are opposite side, there will be cancelled. For example, if it is what happened +1, this will be what? -1. And resulting dipolement will be 0. So now it is non-polar. It is what? Non-polar. Right? Actually, they're having bonds are polar. These are polar bonds only. The bonds are what? Polar only. But resulting dipolement, if you observe, net dipolement, if you observe, will be 0. Why? Because they are cancelled with each other. You can say water. Sir, water also may be cancelled. No, why you are not saying what? Water, mu is you are saying something 1.85 dB. How we got 1.85 dB? Why not 0 here? Here also what happened? You say positive character. Isn't what? Negative character. Again, positive character, negative. Now, what happened here? In this way. What happened here actually? In this way. Now, actually, in this case, what is happening here? The lone pair is there. Then here we don't have any lone pair on the beryllium here. In this case, what happened? Both are moving towards oxygen here. Both are moving towards oxygen. Now, how much it is actually? Maybe something about +1. And it is also moving same in this direction, not opposite direction. It will be +1. So total how much it will be? +2 actually. So here you can't say what happens 0 here. For example, you go for what? One more structure, BF3. BF3. Now again it is positive charge. This one will be the negative charge. This one will be also negative charge. Now it is moving in this direction. Now it is moving in this direction. Now both are opposite, no? If it is +1, this will be -1. Similarly, what happened? This is a negative charge. This is a positive charge. Now again moving in this direction. Now here also these two are what? Opposite side. If it is -1, this will be +1. So here also net dipole moment in this case 0. So polar bonds are there. So I can say BF3 and beryllium fluoride both are having bonds are polar bonds. Bonds are polar bonds. They are having polar bonds. But net dipole moment is cancelled with each other and giving out 0. Water is having 1.85 dBA, where BF3 and BF2 they are having what? 0 dipole moment. Okay, this is about some examples I have taken. Tomorrow class I will complete this topic. Okay, dipole moment is very, very important. Tomorrow I will complete the remaining topics are there. Some examples are there given. So tomorrow let me see that remaining examples here. You have any doubts?